For over a century, we've been told that nothing in the universe can travel faster than light. They say 300,000 kilometers per second is the ultimate cosmic speed limit. It's been drilled into us through textbooks, documentaries, and science classes. But what if I told you that this fundamental truth might not be as absolute as we think? Today we're diving into one of the most mind-bending mysteries in modern physics. Is the speed of light really the fastest thing in the universe? And here's something I'm genuinely curious about. If you could break the speed of light for just one journey, where in the universe would you go? Let me know in the comments below. I will pin the most creative answer. Now let's begin. First, let's establish what we actually mean when we say the speed of light, because light itself isn't always the fastest thing, even in our everyday experience. Light travels at different speeds through different materials. In a vacuum, it blazes along at precisely 299,792,458 meters per second. But when light enters water, it slows down to about 225 million meters per second. In glass, it drops even further to around 200 million meters per second. This slowing happens because photons interact with atoms in the material, getting absorbed and re-emitted countless times. The denser the material, the more these interactions slow light's effective speed. In some exotic materials created in laboratories, scientists have slowed light to a crawl, just 17 meters per second in one famous experiment at Harvard using ultra-cold sodium atoms. But here's where it gets interesting. While light slows down in materials, other particles don't slow down as much. This creates a phenomenon that seems to violate the cosmic speed limit, at least at first glance. When a charged particle like an electron moves through water faster than light moves through that same water, something spectacular happens. The particle creates a shockwave of light, similar to the sonic boom created when an aircraft exceeds the speed of sound. This ethereal blue glow is called Cherenkov radiation, and you can see it in nuclear reactor pools where high-energy particles zip through the cooling water. Wait, you might be thinking, doesn't this mean those particles are traveling faster than light? Yes and no, they're traveling faster than light in that medium, but they're still moving slower than light in a vacuum. It's like saying you're swimming faster than a runner who's jogging through molasses. Impressive, but not breaking any fundamental laws. This distinction is crucial because it shows how carefully we need to think about speed limits in physics. The universal constant isn't just the speed of light, it's the speed of light in a vacuum, the speed of causality itself, the maximum rate at which information can propagate through space-time. But even this carefully defined limit might not be as absolute as we once believed. Let me tell you about quantum entanglement, a phenomenon so strange that Einstein himself called it spooky action at a distance. Imagine you have two particles that become entangled through quantum interaction. These particles are now connected in a way that defies classical intuition. You can separate them by any distance, meters, kilometers, even light years, and they remain mysteriously linked. When you measure a property of one particle, like its spin, you instantly know the corresponding property of its partner, no matter how far away it is. And when I say instantly, I mean faster than light could travel between them. Experiments have confirmed this countless times. In 2017, Chinese scientists used the Multiverse quantum satellite to demonstrate entanglement between particles separated by over 1,200 kilometers. The correlation between measurements happened at least 10,000 times faster than light could have carried a signal between them. This seems to shatter the speed limit completely. Information about one particle's state appears to teleport instantaneously to its entangled partner. How is this possible if nothing can travel faster than light? The answer lies in what we mean by information. While the correlation between entangled particles happens instantly, you can't use this phenomenon to send a message faster than light. The results of measurements appear random at both ends until you compare them, which requires classical communication limited by light speed. It's like having two magic coins that always land on opposite sides, heads and tails, no matter how far apart they are. The correlation is instant, but you can't control which coin shows heads, so you can't send information. Still, this instantaneous correlation disturbed physicists for decades. How does one particle know what its partner is doing faster than light could inform it? The modern understanding involves accepting that entangled particles aren't separate entities communicating across space. They're parts of a single quantum system that exists in a superposition of states until measured. The measurement doesn't send information across space, it reveals information that was always encoded in the system's quantum state. But quantum mechanics has more surprises. Let's talk about quantum tunneling, another phenomenon that seems to mock the speed of light. In classical physics, if you roll a ball toward a hill without enough energy to reach the top, it rolls back down. Simple. But in quantum mechanics, particles can tunnel through barriers they shouldn't be able to cross. An electron approaching an energy barrier has a small probability of appearing on the other side without ever having enough energy to go over the top. This isn't science fiction, it's how the sun works. Protons in the sun's core don't have enough energy to overcome their mutual electrical repulsion and fuse together, but quantum tunneling allows them to bypass this barrier, enabling the nuclear fusion that lights up our star. Without quantum tunneling, the sun wouldn't shine, and we wouldn't exist. Here's where it gets weird. Some experiments suggest that quantum tunneling might happen faster than light. In 2020, researchers at the University of Toronto measured how long it takes for atoms to tunnel through a barrier. Their results suggested the tunneling process took essentially zero time. The atoms appeared on the other side instantaneously. Other experiments have reached similar conclusions. When particles tunnel through barriers, they seem to do so without spending any time inside the barrier itself. It's as if they teleport from one side to the other, crossing the forbidden region faster than light could traverse the same distance. But before we declare the speed of light defeated, we need to be careful about what's actually happening. The particles aren't carrying information through the barrier faster than light. The tunneling process is probabilistic. You can't control when or if a particle will tunnel. And the measurement of tunneling time is itself controversial, with different definitions giving different results. What these experiments really show is that our classical intuitions about motion through space don't apply at quantum scales. Particles don't have well-defined trajectories through barriers. They exist in superpositions of being on both sides until the quantum state collapses. The apparent faster-than-light motion might be an artifact of trying to assign classical properties like position and velocity to inherently quantum phenomena. Speaking of the dangers of pushing cosmic limits, if you're fascinated by what happens when we approach light speed, you should check out my video Why Traveling at the Speed of Light Could Destroy the Universe. It explores the catastrophic consequences of actually reaching that ultimate velocity, from infinite energy requirements to the breakdown of causality itself. The link is in the description, and trust me, it'll change how you think about Einstein's famous limit. Now let's venture into even stranger territory. What about the expansion of space itself? Here's a fact that might blow your mind. Most of the galaxies we can see are currently moving away from us faster than the speed of light, not because they're zooming through space at superluminal velocities, but because space itself is expanding between us and them. This isn't a violation of relativity because the galaxies aren't moving through space faster than light. Space is expanding, carrying them along like raisins in rising bread dough. The farther away a galaxy is, the more space exists between us, and the faster that space expands. Beyond a certain distance called the Hubble radius, about 14 billion light-years away, galaxies recede faster than light speed. We can still see these galaxies because we're seeing them as they were billions of years ago when they were closer and receding slower. But any light they emit now will never reach us. They've crossed a cosmic event horizon, passing forever beyond our ability to communicate with them. The expansion rate is measured by the Hubble constant, roughly 70 kilometers per second per megaparsec. This means for every megaparsec, about 3.26 million light-years, of distance, space expands by 70 kilometers per second. Stack up enough megaparsecs and the expansion exceeds light speed. During cosmic inflation, the exponential expansion phase in the universe's first fraction of a second, space expanded far faster than light. In just 10 to the negative 32 seconds, a region smaller than a proton inflated to larger than a grapefruit. That's an expansion factor of at least 10 to the 26, making light speed look glacial by comparison. This faster-than-light expansion doesn't violate relativity because relativity limits motion through space, not the expansion of space itself. It's a loophole that the universe exploits on the grandest scales. But wait, there's more. Let's talk about phase velocity and group velocity, two concepts that regularly exceed light speed without breaking any laws. Imagine ocean waves approaching a beach. The individual wave crests move at one speed, phase velocity, while the energy of the wave packet moves at another speed, group velocity. In certain situations, the phase velocity can exceed the speed of light, while the group velocity, which carries information and energy, remains subluminal. This happens with light waves in certain materials with anomalous dispersion. The peaks and troughs of the electromagnetic wave can zip along faster than c, but you can't use this to send information faster than light because the wave packet carrying the actual signal still respects the speed limit. Scientists have created elaborate demonstrations of superluminal phase velocities. In some experiments, pulses of light appear to exit a material before they finish entering it, seeming to travel backward in time. But careful analysis shows that no information actually travels faster than light. It's an illusion created by the reshaping of the wave packet. Now let's explore something even more exotic. Tachyons, the hypothetical particles that always travel faster than light. In 1967, physicist Gerald Feinberg proposed that Einstein's equations don't actually forbid faster-than-light particles. They only forbid accelerating from below light speed to above it. But what if particles existed that were always faster than light? These hypothetical tachyons would have bizarre properties. Their mass would be imaginary in the mathematical sense, involving the square root of -1. They would lose energy as they accelerated, approaching infinite speed as their energy approached zero. Time would run backward for tachyons from our perspective. If tachyons exist, they could carry information into the past, creating causality paradoxes. You could receive a message before it was sent, potentially allowing you to prevent it from being sent in the first place. This grandfather paradox for information is one reason many physicists doubt tachyons exist. Despite decades of searching, no experiment has detected tachyons. Every particle we've discovered obeys the light speed limit, but the mathematical possibility remains tantalizing. Perhaps tachyons exist, but don't interact with ordinary matter in ways we can detect. Or perhaps the universe has built-in mechanisms to prevent paradoxes, hiding tachyons from our instruments. The search continues at particle accelerators and cosmic ray detectors. Finding a tachyon would revolutionize physics, but most physicists bet against their existence. The universe seems to protect causality zealously. Let's shift to another phenomenon that pushes the boundaries, the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre showed that Einstein's equations allow for a peculiar solution. By warping space-time in just the right way, contracting it in front of a spacecraft and expanding it behind, You could create a warp bubble that carries the craft faster than light without the craft moving through space at all. Inside the bubble, space would be flat and normal. The crew would feel no acceleration. But the bubble itself could traverse vast distances in arbitrarily short times. It's not science fiction, it's a legitimate solution to Einstein's field equations. The catch? You'd need exotic matter with negative energy density to create the warp bubble. We're talking about matter that gravitationally repels rather than attracts, something we've never observed. Early calculations suggested you'd need more negative energy than the mass energy of the entire observable universe. Recent refinements have reduced the energy requirements, but they're still astronomical. Some proposals suggest using microscopic warp bubbles for communication rather than transportation. Others explore whether quantum effects might naturally create tiny warp bubbles at subatomic scales. NASA's EagleWorks laboratory has actually conducted small-scale experiments attempting to detect space-time distortions that might indicate warp effects. While they haven't built a functioning warp drive, they're taking the theoretical possibilities seriously enough to investigate. The fact that serious scientists at NASA are even considering faster-than-light travel shows how our understanding continues to evolve. But perhaps the most intriguing challenges to light's supremacy come from cosmology itself. Let me tell you about cosmic inflation and why it suggests our universe might have some very strange properties. During inflation, which lasted from about 10 to the negative 36 to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26. Some models suggest even more dramatic expansion. This means regions of space that were causally connected before inflation ended up separated by distances that light couldn't traverse in the age of the universe. This creates what's called the horizon problem. The cosmic microwave background radiation looks almost identical in all directions, with the same temperature to within 1 part in 100,000. But regions on opposite sides of the sky are separated by distances greater than light could have traveled since the Big Bang. How did they coordinate their temperatures? Inflation solves this by proposing that these regions were in causal contact before inflation, then were driven apart faster than light by expanding space. But this solution raises its own questions. What drove inflation? Why did it stop? And most mysteriously, what exactly was inflating? The inflaton field, the hypothetical quantum field responsible for inflation, would have had properties unlike anything we observe today. It would have driven space to expand exponentially, overwhelming all other forces. Some theorists propose that quantum fluctuations in the inflaton field could have created regions of space expanding at different rates, potentially spawning separate pocket universes with different physical properties. If this eternal inflation model is correct, our observable universe is just one bubble in an infinite multiverse. Other bubbles might have different constants of nature, different numbers of dimensions, even different laws of physics. The speed of light might not be universal. It might be a local property of our particular bubble. This brings us to variable speed of light, VSL theories proposed by physicists like João Magalhães and Andreas Albrecht. What if the speed of light isn't constant, but changes over cosmic time? VSL theories can solve some of the same problems as inflation. If light traveled much faster in the early universe, distant regions could have been in causal contact without needing inflation. As the universe evolved, the speed of light could have decreased to its current value. This sounds radical, but it's not without precedent. Other constants of nature might vary. Some observations of distant quasars suggest the fine structure constant, which determines the strength of electromagnetic interactions, might have been slightly different billions of years ago. If one constant can vary, why not others? The implications would be profound. Our entire understanding of cosmology assumes the speed of light has been constant throughout cosmic history. If it varied, we'd need to recalculate the age of the universe, the distance to galaxies, the rate of expansion, everything. Critics argue that VSL theories are unnecessarily complicated and create more problems than they solve. How exactly would the speed of light change? What mechanism would drive this change? And how do you reconcile it with the beautiful simplicity of Einstein's relativity? The debate continues, but it illustrates an important point. Even our most fundamental assumptions about the universe are subject to revision. Science progresses by questioning everything, even the speed of light itself. Now let's examine some actual observations that seem to show faster-than-light motion. Astronomers have observed jets from quasars and other cosmic objects that appear to move across the sky faster than light speed. This superluminal motion was first detected in the 1970s and caused quite a stir. The explanation turned out to be geometric rather than physical. These jets are moving at significant fractions of light speed almost directly toward us. Due to light travel time effects and projection angles, they appear to move sideways across the sky faster than light. It's an optical illusion, but a persistent one that fooled astronomers for years. Similar effects occur in gamma-ray bursts, the most energetic explosions in the universe. Some burst afterglows appear to expand faster than light speed. Again, this is usually explained by geometric effects or by the fact that we're seeing different parts of an expanding shell light up at different times. But not all superluminal observations are so easily explained. Let's talk about quantum experiments that continue to puzzle physicists. In 2018, researchers at the University of Queensland demonstrated that the quantum wave function, the mathematical entity that describes a particle's quantum state, can propagate faster than light under certain conditions. They showed that the peak of a quantum wave packet could arrive at a detector before a classical signal traveling at light speed. This doesn't mean particles themselves traveled faster than light. The wave function isn't a physical object but a probability distribution. Still, the experiment highlights how quantum mechanics continues to surprise us with phenomena that seem to violate our classical intuitions about speed limits. Another puzzling observation comes from cosmology. The universe appears to be flat to within observational error, meaning parallel lines remain parallel even over cosmic distances. But for the universe to be so perfectly flat, different regions must have coordinated their expansion rates to incredible precision. How did they do this if they were never in causal contact? One solution is that the universe is actually infinite in extent. In an infinite universe, our observable patch is just a tiny sample. The flatness we observe might be a local accident in an infinite cosmos with varying curvature. But an infinite universe raises its own paradoxes and challenges to the speed of light. In an infinite universe with infinite matter, every possible quantum state would be realized somewhere. There would be infinite copies of you, reading infinite variations of this script. Information patterns would repeat across vast distances, creating a kind of cosmic redundancy that challenges our notions of uniqueness and causality. Some physicists propose that the universe might be finite but unbounded like the surface of a sphere. Light could circumnavigate such a universe, potentially creating observable patterns in the cosmic microwave background. Searches for these patterns have so far come up empty, suggesting the universe is either infinite or much larger than our observable patch. The mysteries deepen when we consider dark energy, the mysterious force causing the universe's expansion to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy comprises about 68% of the universe's energy density, yet we have no idea what it actually is. If these cosmic mysteries give you chills like they give me, make sure to subscribe. I'm dropping mind-blowing space content every week that you won't find anywhere else. and smash that like button. It genuinely helps more curious minds discover these videos. Takes 2 seconds, makes all the difference. Dark energy's effects become dominant on large scales, pushing galaxies apart faster and faster. Eventually, if dark energy continues its current behavior, all galaxies outside our local group will accelerate beyond the cosmic horizon. They'll be receding faster than light, lost to us forever. The observable universe will shrink even as the actual universe expands. This creates a profound limit on future knowledge. Civilizations arising billions of years from now will see a much emptier universe. Evidence of the Big Bang, cosmic expansion, and other galaxies will have literally disappeared beyond the light-speed horizon. They might conclude they live in a static, eternal universe containing only their local group of galaxies. We're lucky to exist at a cosmic moment when so much is still visible. But it also means there might be aspects of the universe already beyond our horizon, racing away faster than light can bring us information about them. What cosmic truths are we missing because they've already passed beyond our ability to observe? Let's dive into another phenomenon that challenges our understanding: the quantum Zeno effect. This bizarre quantum mechanical effect suggests that frequent observation can freeze a quantum system in place, preventing it from evolving. It's like the watched pot that never boils, except it's real and happens at quantum scales. In some interpretations, the quantum Zeno effect involves faster-than-light influences. The act of measurement seems to instantaneously collapse the wave function across all of space, determining the particle's properties everywhere at once. How does the wave function know to collapse simultaneously at distant locations? This touches on the measurement problem, one of the deepest mysteries in quantum mechanics. When exactly does a quantum superposition collapse into a definite state? How does the universe decide which outcome to manifest? Some theories propose that consciousness plays a role, others invoke decoherence through environmental interaction, and still others suggest all possibilities remain real in parallel universes. Each interpretation has different implications for faster-than-light effects. In the many-worlds interpretation, no faster-than-light communication occurs because all outcomes happen in separate branches of reality. In collapse theories, something must coordinate the collapse across space, potentially involving superluminal effects we don't yet understand. Recent experiments have pushed these questions to new extremes. Scientists have created quantum superpositions of larger and larger objects, molecules with thousands of atoms, tiny mechanical resonators, even small diamonds. As these experiments scale up, they probe whether there's a fundamental limit where quantum effects give way to classical behavior. Some theories propose that gravity itself might cause wave function collapse, providing a natural boundary between quantum and classical realms. If true, this could involve faster-than-light gravitational effects that maintain consistency across space. We're entering uncharted territory where quantum mechanics, gravity, and the speed of light intersect in ways we're only beginning to explore. Now let's talk about something that might sound like pure science fiction, but is grounded in serious physics: closed, time-like curves. These are paths through space-time that loop back to their own past, potentially allowing faster-than-light communication through time travel. General relativity, Einstein's theory of gravity, allows for closed, time-like curves under certain conditions. Rotating black holes, cosmic strings, and traversable wormholes could all potentially create regions where time loops back on itself. An observer following such a curve could arrive at their own past, effectively traveling faster than light by taking a shortcut through time. The most famous example is the Alcubierre metric I mentioned earlier, but there are others. The Van Stockham spacetime, describing an infinitely long rotating cylinder, allows closed, time-like curves. The Gödel universe, a rotating cosmological solution discovered by mathematician Kurt Gödel, permits time travel throughout the entire cosmos. These solutions disturb physicists because they threaten causality. If you could travel to your own past, you could create paradoxes, preventing your own birth, killing your grandfather, or creating logical contradictions. Physics seems to abhor such paradoxes, leading Stephen Hawking to propose the chronology protection conjecture. The universe always prevents the formation of closed, time-like curves. But how exactly does the universe enforce this protection? Some proposals involve quantum effects that destabilize any would-be time machine. Others suggest that self-consistent histories are the only ones that can exist. You can travel to the past, but only in ways that were always part of history. Still others propose that attempting to create paradoxes splits you into a parallel universe, where your actions don't affect your original timeline. The debate remains unresolved, but it highlights how faster-than-light travel and time travel are intimately connected. Any method of exceeding light speed could potentially be configured as a time machine, which might be why the universe seems to forbid both so strictly. Let's examine another cosmic mystery that might involve faster-than-light effects: dark matter. This invisible substance makes up about 27% of the universe's mass energy, yet we can only detect it through its gravitational effects. Despite decades of searching, we haven't directly detected a single dark matter particle. Some theories propose that dark matter interacts through forces other than gravity, perhaps forces that propagate faster than light. If dark matter particles communicate through instantaneous forces, it could explain some puzzling observations about galaxy formation and structure. For instance, galaxies seem to know how much dark matter they contain and adjust their visible matter accordingly. The Tully-Fisher relation shows a tight correlation between a galaxy's rotation speed and its luminosity, suggesting a connection between dark and visible matter that's maintained across the entire galaxy. How do opposite sides of a galaxy separated by hundreds of thousands of light-years coordinate so precisely? One possibility is that dark matter doesn't follow the same rules as ordinary matter. Perhaps it exists partially in extra dimensions where different speed limits apply. Or maybe dark matter particles are connected by quantum entanglement on galactic scales, maintaining correlations that appear faster than light from our limited perspective. The Xenon, Lux, and other dark matter detection experiments have found nothing so far, placing ever tighter constraints on dark matter's properties. This has led some physicists to propose more exotic possibilities. What if dark matter isn't particles at all but modifications to gravity that mimic the effects of invisible mass? The most radical proposal suggests that the black hole interior doesn't exist as we imagine. Instead, information falling toward the horizon gets encoded on the surface itself, creating a holographic representation that appears three-dimensional to outside observers. From this perspective, nothing ever actually crosses the event horizon. It just gets scrambled and encoded in increasingly complex patterns on the boundary. This firewall hypothesis proposes that anyone falling into a black hole would encounter a wall of high-energy radiation at the horizon, not the smooth passage predicted by general relativity. The firewall would incinerate anything attempting to cross, preserving information but violating the equivalence principle that says falling observers shouldn't notice anything special about crossing the horizon. The debate continues, but it highlights how our understanding of space, time, and information remains incomplete. If information can be encoded holographically on surfaces, what does this mean for the speed of information transfer? Perhaps the fundamental limits aren't about motion through space, but about information processing on the boundaries of space-time itself. Now let's venture into the realm of extra dimensions, where the speed of light might not be the universal constant we think it is. String theory, our best attempt at unifying quantum mechanics and gravity, requires additional spatial dimensions beyond the three we experience. These extra dimensions might be curled up so small we can't detect them, or they might be large but accessible only to certain types of particles. In some models, gravity can propagate through extra dimensions, while electromagnetic forces remain confined to our three-dimensional space. This could explain why gravity is so much weaker than other forces. It's diluted by spreading into higher dimensions, but it also suggests that gravitational effects might take shortcuts through extra dimensions, potentially arriving faster than light traveling through ordinary space. The Large Hadron Collider has searched for evidence of extra dimensions by looking for missing energy in particle collisions. If extra dimensions exist, some collision energy could escape into them, appearing as missing momentum in our detectors. So far, these searches have found nothing, placing tight constraints on the size and accessibility of any extra dimensions. But absence of evidence isn't evidence of absence. Extra dimensions might exist, but be inaccessible to the energies we can currently produce. Or they might be accessible only under extreme conditions like those found in black holes or during the first moments after the Big Bang. We're still learning how to probe these possibilities experimentally. Some theories propose that dark matter particles can access extra dimensions while ordinary matter cannot. This could explain why dark matter seems to interact so weakly with normal matter. It's partially existing in dimensions we can't access. If true, dark matter might follow different speed limits than ordinary matter, potentially explaining some puzzling observations about galaxy formation and cosmic structure. The concept of brain-world cosmology takes this further, suggesting that our entire universe is a three-dimensional membrane floating in higher dimensional space. Other brains might exist parallel to ours, containing their own matter and forces. Gravity could propagate between brains, creating subtle effects we might detect through precision measurements of gravitational forces. In some brain world models, the speed of light could vary between different brains or change as brains move relative to each other. Our brain might be drifting through higher dimensional space, causing apparent changes in fundamental constants over cosmic time. This could explain some puzzling observations suggesting that the fine structure constant might have been different in the early universe. Let's explore another frontier where faster-than-light effects might hide: the quantum vacuum itself. Empty space isn't actually empty, but seethes with virtual particles popping in and out of existence on timescales so brief that they can't be directly observed. These quantum fluctuations have measurable effects like the Casimir force between conducting plates and the slight shift in hydrogen energy levels called the Lamb shift. The quantum vacuum might have structure we don't yet understand. Some theories propose that virtual particles can propagate faster than light for brief periods, as long as they don't carry information over macroscopic distances. These superluminal virtual particles could mediate forces or create correlations that appear instantaneous from our perspective. The vacuum might also have different properties in different regions of space or at different energy scales. Near black holes in the early universe, or at the Planck scale where quantum gravity effects dominate, the vacuum structure could be radically different from what we observe in our low-energy environment. These exotic vacuum states might permit faster-than-light propagation under conditions we can't yet create or observe. Recent experiments have probed the quantum vacuum with unprecedented precision. The ALPHA experiment at CERN has measured the gravitational behavior of antimatter, confirming that antihydrogen falls downward just like ordinary matter. But these experiments also open new questions about vacuum structure and whether matter and antimatter interact identically with spacetime. Some theories propose that the vacuum has a preferred reference frame, violating the principle of relativity that says all inertial frames are equivalent. If true, this could create subtle violations of Lorentz invariance. the symmetry that underlies special relativity. Experiments searching for such violations have found nothing so far, but they're pushing the boundaries of measurement precision. The possibility of Lorentz violation connects to theories of quantum gravity, where space-time itself might have granular structure at the Planck scale. If space and time are made of discrete units, like pixels in a digital image, then the smooth symmetries of relativity might be approximations that break down at the smallest scales. This could permit faster-than-light propagation for phenomena that probe the fundamental structure of space-time. Now let's examine one of the most ambitious experiments ever conceived, the search for gravitons, the hypothetical particles that carry gravitational force. If gravity is quantized like other forces, then gravitational waves should be composed of individual gravitons, just as light is composed of photons. Detecting individual gravitons would require sensitivity far beyond current technology. A graviton detector would need to be more massive than Jupiter and more sensitive than our best current instruments by factors of trillions. But the theoretical possibility remains, and some physicists are exploring whether quantum effects might amplify graviton interactions under special conditions. If gravitons exist and can be detected, they might reveal new physics about the speed of gravity. While gravitational waves travel at light speed, individual gravitons might have subtle properties that differ from photons. They might interact with the quantum vacuum differently, or couple to extra dimensions in ways that electromagnetic radiation cannot. The search for gravitons also connects to the quest for a theory of quantum gravity. String theory proposes that gravitons are closed loops of vibrating string, while loop quantum gravity suggests they emerge from the discrete structure of space-time itself. Each approach makes different predictions about graviton properties and their relationship to the speed of light. Some quantum gravity theories propose that space-time itself is emergent from more fundamental quantum information. In these models, space and time aren't fundamental but arise from entanglement patterns in an underlying quantum system. The speed of light would then be a property of how information propagates through these entanglement networks, rather than a fundamental feature of space-time geometry. This information-theoretic approach to space-time suggests that faster-than-light effects might be possible if we could manipulate the underlying quantum information directly. Instead of moving through space faster than light, we might be able to restructure the information patterns that create the appearance of space and distance. This remains highly speculative, but it illustrates how our understanding of reality's foundations continues to evolve. Let's turn to another cutting-edge area, the study of quantum field theory in curved space-time. When quantum mechanics meets general relativity, strange things happen. The vacuum state of quantum fields depends on the space-time geometry, leading to effects like Hawking radiation from black holes and the Unruh effect, where accelerated observers detect thermal radiation in what inertial observers see as empty space. These effects suggest that the speed of light might not be absolute, but could depend on the observer's state of motion and the local space-time geometry. An accelerated observer might see vacuum fluctuations that appear to propagate faster than light, even though inertial observers see nothing unusual. The boundary between what's real and what's observer-dependent becomes blurred in these extreme regimes. The Unruh effect has never been directly observed because the accelerations required to produce detectable thermal radiation are enormous. But some theorists propose that similar effects might occur in other contexts, like near the event horizons of black holes or in the intense electromagnetic fields around neutron stars. These natural laboratories might reveal new physics about the relationship between motion, acceleration, and the speed of light. Quantum field theory also predicts that the vacuum can be polarized by strong electromagnetic fields, creating virtual electron-positron pairs that affect light propagation. In the most intense magnetic fields around magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, these vacuum polarization effects become significant. Light might propagate differently in different directions, potentially at slightly different speeds depending on its polarization. These effects remain tiny and difficult to observe, but they represent genuine modifications to the speed of light in extreme environments. They remind us that even our most fundamental constants might not be truly constant under all conditions. The universe's most extreme environments serve as natural laboratories for testing the limits of our physical theories. Let's dive into one of the most mind-bending aspects of modern cosmology, the multiverse. If our universe is just one of countless others, each with potentially different physical laws, then the speed of light might not be universal at all. It might be a local accident, specific to our cosmic neighborhood. The eternal inflation model suggests that our Big Bang was just one bubble in an eternally inflating multiverse. Different bubbles could have different values for fundamental constants, including the speed of light. In some universes, light might crawl along at the speed of sound. In others, it might race at speeds that make our light seem frozen in comparison. This raises profound questions about the nature of physical law. Are the constants we observe fine-tuned for our existence, or are we simply observing the universe where we happen to exist? The anthropic principle suggests that we find ourselves in a universe compatible with our existence precisely because we couldn't exist in universes with radically different physics. But if the speed of light varies between universes, what determines its value in each one? Some theories propose that constants are set by the way extra dimensions curl up during each universe's formation. Different curling patterns would produce different physics, like tuning knobs on a cosmic radio, selecting different frequencies. The landscape of string theory contains an estimated 10 to the 500th possible vacuum states, each corresponding to a different way the extra dimensions could be configured. Each state would have different particle masses, force strengths, and potentially different speeds of light. Our universe would be just one point in this vast landscape of possibilities. If true, this would revolutionize our understanding of physical law. Instead of seeking the unique theory that describes reality, we'd be mapping a vast space of possible realities, trying to understand why we find ourselves in this particular corner of the landscape. The speed of light wouldn't be a fundamental constant, but an environmental parameter, like the temperature of our planet. Some physicists find this multiverse thinking unsatisfying because it seems to abandon the goal of finding unique, testable predictions. If anything is possible somewhere in the multiverse, how can we ever prove a theory wrong? Others argue that the multiverse is a natural consequence of our best theories, and we should follow the mathematics wherever it leads. The debate touches on deep questions about the nature of scientific explanation. Is it enough to show that our universe is possible, or must we explain why it's actual? Can we ever hope to understand why the speed of light has the value it does, or must we accept it as a brute fact about our cosmic environment? Now let's explore quantum chromodynamics, the theory describing the strong nuclear force that holds protons and neutrons together. This force has a peculiar property. It gets stronger as particles are pulled apart, unlike gravity or electromagnetism, which weaken with distance. This leads to a phenomenon called confinement, where quarks can never be isolated but are always bound together in composite particles. The strong force might seem unrelated to the speed of light, but recent calculations suggest otherwise. Inside protons and neutrons, quarks and gluons zip around at significant fractions of light speed. The internal dynamics of these particles involve relativistic quantum field theory in its full complexity, where virtual particles constantly pop in and out of existence. Some theoretical work suggests that under extreme conditions, like those in the cores of neutron stars or during high-energy particle collisions, the strong force might create regions where the effective speed of light is modified. These would be tiny, fleeting domains where the usual rules of space-time propagation don't apply in the way we expect. The quark-gluon plasma created in heavy ion collisions at the Large Hadron Collider and the relativistic Heavy Ion Collider represents matter in its most extreme state, where individual protons and neutrons melt into a soup of their constituent quarks and gluons. In this plasma, which existed for microseconds after the Big Bang, the normal rules of particle physics are suspended. Measurements of quark-gluon plasma properties have revealed surprising behavior. The plasma flows like a nearly perfect fluid with almost no viscosity, quite different from the gas-like behavior physicists expected. This perfect fluidity might involve correlations that propagate faster than naive expectations would suggest, though still respecting the fundamental light speed limit. The study of quark-gluon plasma connects to broader questions about the nature of space-time at the smallest scales. If space and time have granular structure at the Planck length, about 10 to the negative 35 meters, then the smooth geometry of general relativity would be an approximation that breaks down at these scales. Various approaches to quantum gravity make different predictions about Planck-scale physics. String theory suggests that space-time is woven from vibrating strings in higher dimensions. Loop quantum gravity proposes that space itself is made of discrete loops and nodes, like a cosmic mesh. Causal set theory imagines space-time as a collection of discrete events, connected by causal relationships. Each approach has different implications for the speed of light at fundamental scales. In string theory, the speed might depend on the vibrational modes of the strings and the geometry of extra dimensions. In loop quantum gravity, it might be related to the discrete structure of the space-time mesh. In causal set theory, it might emerge from the statistical properties of causal connections. These quantum gravity effects would be utterly negligible at everyday scales, but might become important in extreme environments like black hole interiors or the first moments of cosmic inflation. They might also accumulate over vast distances, potentially creating observable effects in light from the most distant galaxies. Some experiments are already searching for such effects. The Fermi Gamma Ray Space Telescope looks for tiny delays between high-energy and low-energy photons from distant gamma-ray bursts. If space-time has granular structure, high-energy photons might interact with it differently than low-energy ones, creating measurable delays over cosmic distances. So far, these searches have found no evidence of Planck-scale effects, placing tight constraints on some quantum gravity models. But the absence of effects at current sensitivity levels doesn't rule out all possibilities. More sensitive experiments and longer observation times might yet reveal the granular nature of space-time. Let's examine another frontier where the speed of light meets its limits: the study of cosmic rays, high-energy particles that bombard Earth from space. The most energetic cosmic rays carry more energy than anything we can produce in particle accelerators, reaching energies up to 10 to the 20th electron volts. These ultra-high energy cosmic rays pose puzzles that might involve faster-than-light physics. The GZK cutoff, predicted by physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin in 1966, suggests that cosmic rays above a certain energy threshold should interact with cosmic microwave background photons and lose energy rapidly. This means ultra-high energy cosmic rays shouldn't be able to travel more than about 50 million light-years before being degraded. Yet we observe cosmic rays that seem to violate this prediction, arriving with energies that should be impossible if they originated from distant sources. This GZK paradox might indicate new physics beyond the standard model, possibly involving particles that don't interact with photons in the expected way, or that can somehow bypass the usual energy loss mechanisms. Some exotic explanations involve faster-than-light propagation. If ultra-high-energy cosmic rays can take shortcuts through extra dimensions or exploit exotic space-time geometries, they might arrive with more energy than conventional physics allows. Alternatively, they might be produced by nearby sources we haven't identified, avoiding the GZK cutoff entirely. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah are studying these cosmic ray mysteries with unprecedented precision. They've confirmed that the highest energy cosmic rays do seem to be suppressed, consistent with the GZK cutoff, but puzzles remain about their composition and arrival directions. Recent observations suggest that ultra-high energy cosmic rays might be predominantly heavy nuclei rather than protons, which would modify the GZK cutoff predictions. Heavy nuclei interact differently with cosmic microwave background photons, potentially allowing them to travel farther while maintaining high energies. This might resolve the paradox without requiring exotic physics, but the cosmic ray mystery illustrates how extreme energy phenomena continue to challenge our understanding. At energies approaching the Planck scale, where quantum gravity effects become important, we might discover that the speed of light isn't the absolute barrier we think it is. The universe's most energetic processes serve as natural laboratories for testing the limits of physical law. Now let's explore the fascinating world of metamaterials, artificially engineered structures that can manipulate electromagnetic waves in ways impossible with natural materials. These materials can bend light around objects, creating invisibility cloaks, or focus it beyond the diffraction limit, enabling super-resolution imaging. Some metamaterials have negative refractive indices, meaning light bends the wrong way when entering them. In these materials, the phase velocity of light can exceed the speed of light in vacuum, while the group velocity remains subluminal. This creates the strange situation where wave crests move faster than light, while information still propagates at normal speeds. More exotic metamaterials might manipulate space-time itself rather than just electromagnetic fields. Theoretical proposals suggest that carefully designed structures could create artificial event horizons, regions where the effective speed of light drops to zero. Such optical black holes could trap light completely, creating perfect absorbers for specific wavelengths. Other metamaterial designs might create regions of negative energy density, the exotic matter needed for wormholes and warp drives. While the energy scales involved would be tiny, these experiments could test whether the exotic matter required for faster-than-light travel can actually exist in nature. The field of transformation optics uses metamaterials to create artificial space-time geometries for electromagnetic waves. Light propagating through these materials experiences curved paths as if space-time itself were warped. This allows researchers to simulate black holes, wormholes, and other exotic space-time geometries in tabletop experiments. These optical analogues can't create actual faster-than-light travel, but they can test our understanding of how light behaves in curved space-time. They might reveal new phenomena that could apply to real gravitational systems, potentially uncovering loopholes in our understanding of the speed of light barrier. Metamaterials also enable the study of quantum effects in artificial spacetimes. Researchers have created optical analogues of Hawking radiation, the Unruh effect, and other quantum field theory phenomena. These experiments probe the boundary between quantum mechanics and general relativity in controlled laboratory settings. The ultimate goal is to create metamaterials that can manipulate space-time itself rather than just electromagnetic fields. This would require materials that interact with gravity in controllable ways, something far beyond current technology. But the theoretical foundations are being laid through our growing understanding of how matter and energy curve space-time. Some proposals involve using metamaterials to amplify tiny quantum fluctuations in space-time, potentially creating measurable gravitational effects from microscopic sources. Others explore whether metamaterials could create artificial cosmic strings or other topological defects in space-time. These remain highly speculative, but they illustrate how our understanding of space, time, and matter continues to evolve. Let's turn to another cutting-edge area, the study of time crystals, exotic states of matter that repeat in time rather than space. Discovered in 2012 by Nobel laureate Frank Wilczek, time crystals break time translation symmetry while remaining in their ground state, creating perpetual motion without energy input. Time crystals might seem unrelated to the speed of light, but they challenge our understanding of time itself. If matter can have temporal structure that repeats periodically, what does this mean for the flow of time and the propagation of information? Some theoretical work suggests that time crystals might enable new forms of quantum information processing that exploit temporal correlations. The creation of time crystals in laboratory settings has opened new avenues for studying the nature of time. These systems exist in quantum superpositions that oscillate forever without losing energy, creating temporal patterns that persist indefinitely. They might provide new insights into how time emerges from more fundamental quantum processes. Some speculative theories propose that space-time itself might have crystalline structure with regular patterns in both space and time. If true, this could create preferred reference frames that violate the principle of relativity, potentially allowing faster-than-light effects under special conditions. These ideas remain highly theoretical, but they illustrate how our understanding of time continues to evolve. The study of time crystals also connects to broader questions about the arrow of time and the second law of thermodynamics. Why does time flow in one direction? Why do we remember the past but not the future? Time crystals exist in states that seem to violate our intuitions about temporal flow, potentially offering new perspectives on these fundamental questions. Recent experiments have created time crystals in various physical systems, from trapped ions to superconducting circuits. Each system reveals different aspects of temporal crystalline order, building our understanding of how time and matter can interweave in unexpected ways. These discoveries might eventually lead to new technologies that exploit temporal correlations for quantum computing or communication. Let's venture into one of the most perplexing realms of modern physics, the measurement problem in quantum mechanics and its potential connection to faster-than-light effects. When we measure a quantum system, its wave function appears to collapse instantaneously across all of space, determining the particle's properties everywhere at once. This collapse seems to happen faster than light could travel between distant locations. Consider the delayed choice quantum eraser experiment, one of the most mind-bending demonstrations in physics. Photons are split into entangled pairs and sent along different paths. One photon hits a detector immediately, while its partner travels a much longer route. The crucial twist is that you can choose whether to measure which path the distant photon took, even after its partner has already been detected. Remarkably, your future choice about the distant photon retroactively determines whether the already detected photon shows wave-like or particle-like behavior. It's as if information about your measurement decision travels backward in time to influence events that already happened. This suggests that quantum correlations transcend our normal understanding of space and time. The implications are staggering. If quantum measurements can influence past events, what does this mean for causality and the speed of light? Some interpretations propose that quantum mechanics operates outside normal space-time, in a realm where past, present, and future are equally real and accessible. The wave function collapse wouldn't involve faster-than-light communication, but rather the revelation of timeless correlations. Other interpretations avoid these paradoxes by denying that wave function collapse is a physical process. In the many-worlds interpretation, all possible measurement outcomes occur in parallel universes. There's no collapse, no faster-than-light effects, and no violation of causality, just an infinite branching of reality into every possible configuration. But even many worlds raises puzzling questions about the speed of light. If every quantum event splits the universe into multiple branches, how fast does this splitting propagate? Does it happen instantaneously throughout space, or does it spread at light speed? The mathematics of quantum mechanics doesn't specify, leaving us with deep uncertainties about the nature of reality itself. Recent experiments have pushed these questions to new extremes. Scientists have demonstrated quantum superposition in increasingly large objects, from molecules to tiny mechanical resonators. As these experiments scale up, they probe whether there's a fundamental boundary where quantum effects give way to classical behavior. Some theories propose that gravity itself causes wave function collapse, providing a natural mechanism for the quantum to classical transition. If true, this would involve gravitational effects that somehow coordinate across space to maintain consistency. The speed at which gravitational information propagates becomes crucial for understanding how this coordination works. The relationship between quantum mechanics and gravity remains one of physics' greatest unsolved problems. General relativity describes gravity as curved spacetime, while quantum mechanics treats it as exchanged particles called gravitons. These approaches make different predictions about faster-than-light effects and the nature of spacetime itself. String theory attempts to unify these perspectives by describing all particles, including gravitons, as vibrating strings in higher dimensional space. In string theory, the speed of light emerges from the fundamental properties of string vibrations and the geometry of extra dimensions. Different string configurations could potentially support different light speeds. Loop quantum gravity takes a different approach, proposing that space-time itself has discrete structure at the Planck scale. In this picture, space is woven from quantum loops, and time emerges from the evolution of these quantum states. The speed of light would be related to how quickly information can propagate through this quantum space-time mesh. Both approaches suggest that our understanding of the speed of light might be incomplete. At the Planck scale, where quantum gravity effects dominate, the smooth space-time of general relativity breaks down. New physics might emerge that allows faster-than-light propagation under extreme conditions we can't yet create or observe. Let's explore another frontier where faster-than-light effects might hide, the study of consciousness and its relationship to quantum mechanics. Some researchers propose that consciousness involves quantum processes in the brain that might exploit faster-than-light correlations. The orchestrated objective reduction theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum computations in microtubules within brain cells. These quantum processes might involve non-local correlations that transcend the normal speed of light limitations. If consciousness involves quantum entanglement across different parts of the brain, this could explain the unity of conscious experience. How does the brain integrate information from millions of neurons into a single, coherent experience? Quantum correlations might provide the binding mechanism that creates unified consciousness from distributed neural activity. This remains highly speculative, and most neuroscientists doubt that quantum effects play significant roles in brain function. The brain seems too warm and noisy to maintain the delicate quantum states required for such processes. But some experiments have found quantum effects in biological systems, from photosynthesis to bird navigation, suggesting that life might exploit quantum mechanics in unexpected ways. If consciousness does involve quantum processes, this could have profound implications for our understanding of reality. Conscious observation plays a central role in quantum mechanics, determining when and how wave functions collapse. If consciousness itself operates through quantum mechanisms, this creates a strange loop where quantum effects influence consciousness, which in turn influences quantum effects. Some interpretations of quantum mechanics propose that consciousness is fundamental to reality, not just an emergent property of complex brains. In these views, the universe is inherently conscious, and what we call physical reality emerges from conscious observation and choice. The speed of light might not be a fundamental limit, but rather a constraint that emerges from the structure of conscious experience. These ideas venture far beyond mainstream physics, but they illustrate how the mysteries of quantum mechanics continue to challenge our understanding of reality. The relationship between mind and matter, consciousness and cosmos, remains one of the deepest puzzles in science. Now let's examine another exotic possibility: the idea that the universe might be a simulation running on some vast computational system. If our reality is digital, what would this mean for the speed of light and other physical constants? In a simulated universe, the speed of light might simply be the maximum rate at which information can propagate through the computational substrate. Just as video games have maximum frame rates and processing speeds, a simulated universe might have fundamental limits determined by its underlying hardware. This simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that advanced civilizations might run detailed simulations of their ancestors or alternative histories. If computational power continues to grow exponentially, future civilizations might have the resources to simulate entire universes with conscious inhabitants. From inside such a simulation, the speed of light would appear to be a fundamental constant of nature. But from outside, it would be an artifact of the simulation's design. The programmers could potentially modify physical constants, create regions with different physics, or even pause and restart the simulation without the inhabitants noticing. Some physicists have proposed tests for the simulation hypothesis. If space-time has discrete structure at the smallest scales, this might be evidence of digital reality. Certain patterns in cosmic ray distributions or subtle glitches in physical laws might reveal the computational nature of reality. The simulation hypothesis also raises questions about faster-than-light travel. If our universe is simulated, the programmers might have access to the underlying computational substrate, allowing them to move information or even conscious beings between different parts of the simulation faster than the simulated speed of light allows. This connects to broader questions about the nature of information and computation. Is the universe fundamentally computational, with physical processes equivalent to information processing? Some theories propose that reality is made of information, with matter and energy as emergent properties of underlying computational processes. If true, this would revolutionize our understanding of the speed of light. Instead of being a fundamental feature of space-time, it might be a constraint on information processing in the cosmic computer that runs our reality. Faster-than-light effects might be possible if we could access deeper levels of the computational hierarchy. Let's explore another cutting-edge area, the study of topological phases of matter and their potential connection to faster-than-light phenomena. Topological materials have properties that are protected by their global structure rather than local details, making them remarkably robust against perturbations. Some topological materials support exotic quasi-particles called anyons, which have properties intermediate between bosons and fermions. Certain types of anyons, called non-abelian anyons, could potentially be used for topological quantum computing, where information is stored in the global properties of the quantum state rather than in individual particles. The fascinating aspect of topological protection is that it seems to involve instantaneous correlations across the entire system. When you try to change a topological property locally, the system responds globally to maintain its protected state. This global response appears to happen faster than light could travel across the system. However, like quantum entanglement, these topological correlations don't allow faster-than-light communication. You can't use them to send information because the correlations are built into the system's structure rather than being controllable signals. Still, they represent another example of how quantum systems can maintain correlations that transcend classical space-time limitations. Recent discoveries in topological materials have revealed new phases of matter with exotic properties. Topological insulators conduct electricity on their surfaces while remaining insulating in their bulk. Topological superconductors might host Majorana fermions, particles that are their own antiparticles, and could be used for fault-tolerant quantum computing. Some theoretical work suggests that topological phases might exist in space-time itself, not just in condensed matter systems. If space-time has topological structure, this could create protected channels for information propagation that bypass normal speed-of-light limitations. These topological space-time phases remain highly speculative, but represent an active area of research. The study of topological materials also connects to our understanding of the quantum vacuum. The vacuum might have topological structure that we don't yet understand, with protected modes that could support faster-than-light propagation under special conditions. These vacuum topological phases could be the key to understanding how quantum entanglement maintains its instantaneous correlations. Now let's delve into the mysterious world of dark energy and its potential relationship to faster-than-light phenomena. Dark energy, which comprises about 68% of the universe's energy density, is causing the expansion of space to accelerate. This acceleration means that distant galaxies are receding from us at ever-increasing speeds. The nature of dark energy remains completely unknown. It could be a cosmological constant, a fundamental property of space-time itself, or it might be a dynamic field that changes over time, potentially affecting other physical constants, including the speed of light. Some theories propose that dark energy is actually a manifestation of extra dimensions or modifications to gravity on cosmic scales. If dark energy is dynamic, it might create regions of space with different expansion rates or even different physical laws. In some models, dark energy could create bubble universes with varying properties, including different speeds of light. Our observable universe might be just one bubble in a vast foam of cosmic domains. The accelerating expansion driven by dark energy also creates a cosmic event horizon. Galaxies beyond a certain distance are receding faster than light and will eventually disappear from our observable universe. This shrinking of the observable cosmos means that future civilizations will have access to less information about the universe's history and structure. But dark energy might also create opportunities for faster-than-light effects. Some theories propose that dark energy fields could be manipulated to create regions of negative energy density, the exotic matter needed for wormholes and warp drives. If we could harness dark energy, we might be able to engineer space-time itself. The relationship between dark energy and quantum mechanics remains poorly understood. Dark energy might emerge from quantum fluctuations in the vacuum, though calculations suggest this should produce effects trillions of times larger than observed. This cosmological constant problem is one of the greatest unsolved puzzles in physics. Some solutions to the cosmological constant problem involve anthropic reasoning. We observe a small cosmological constant because larger values would prevent galaxy formation and the evolution of life. In a multiverse with varying dark energy densities, we necessarily find ourselves in a region compatible with our existence. But this anthropic explanation raises troubling questions about the nature of physical law. If fundamental constants are environmental accidents rather than deep principles, what hope do we have of understanding why the universe works the way it does? The speed of light might be just another arbitrary parameter in our cosmic neighborhood. Recent observations have begun to probe dark energy's properties with increasing precision. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and future missions like the Nancy Grace Roman Space Telescope are mapping the universe's expansion history in unprecedented detail. These observations might reveal whether dark energy is truly constant or evolves over cosmic time. If dark energy is evolving, this could have profound implications for the speed of light and other fundamental constants. Some theories link dark energy to scalar fields that could affect the properties of matter and radiation. Changes in these fields might cause apparent variations in the speed of light over cosmic time. The study of dark energy also connects to the search for quantum gravity. If dark energy emerges from quantum space-time fluctuations, understanding its nature might require a complete theory of quantum gravity. This theory might reveal new physics that allows faster-than-light propagation under conditions we haven't yet imagined. If you made it this far, make sure to give a like and subscribe to the channel. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Does gravity really travel faster than light? In this video, we unravel one of the most profound questions in physics. How fast does gravity move? And what does that reveal about the fabric of space-time? See you there.